In this lecture, we're going to talk about quadratic equations, that is, equations with one variable that are second degree. In other words, polynomials whose biggest exponent is 2. Now, before we start, I want to be clear on exactly what we mean by a quadratic equation. A quadratic equation is one that looks like this. It's ax squared plus bx plus c, where a is not equal to 0. And the last part is important because if we let a equal 0, then that would make this whole first term 0, and our equation will become just a linear equation. Now, unlike linear equations, where there really is one approach to solving them that works all the time, quadratic equations are a little more complicated. We have some methods, like the factoring method we're going to talk about here, that are relatively simple to use, but that only work for some equations. And we have more complicated methods, like the quadratic formula, which we'll talk about on a later slide, that aren't as easy to use, but that work all the time. So to solve a quadratic equation by factoring, all you have to do is factor the polynomial, then set each of the individual factors equal to 0. The solutions to those smaller equations will also be the solutions of the original equation. So, looking at this first problem, this factors to x plus 3 times x plus 1. And if I set those factors equal to 0, I get two linear equations. X plus 3 equals 0. And x plus 1 equals 0. The solutions to those equations are x equals negative 3 and x equals negative 1. So those will also be the solutions of the original equation. Now the second equation is a little different because it isn't equal to 0. It's equal to 6. Now before you start using this factoring method, you have to make sure the equation is equal to 0. To get this equation into that form, I'll just subtract 6 from both sides. Now I can factor the left-hand side to 2x minus 3 times x plus 2. And if I set those factors equal to 0, I get two linear equations. And if I solve those equations, I get x equals negative 2 and x equals 3/2, which will also be the solutions of the original equation. Now, this third equation illustrates a situation where the factoring method runs up against a wall. There isn't any obvious way to factor this polynomial, so the factoring method isn't any use to us here. To solve this equation, we'll have to use one of the other methods that we'll discuss in the coming slides. Now, the square root method is another method that's really easy to use, but that only works in the special case where we have the variable part being squared and a number. So, for example, in this first equation, I can solve this by adding 81 to both sides. Now, this equation I can solve using the square root part of the square root method. I can eliminate the exponent on the x by taking the square root of both sides. The square root of x squared is just x. And on the right side, I'll have plus or minus 9. Now, that plus or minus part is an important part that's easy to forget. Remember that whenever you take the square root of an equation, you're going to get two solutions, both the positive and a negative one. In this case, that's because 9 squared is 81, and negative 9 squared is also 81. Now, with the second equation, notice how I have something squared minus a number. To use our square root method here, I'll start by adding 3 to both sides. Then I'll take the square root of both sides. That will give me x plus 2 equals plus or minus the square root of 3. And finally, I'll subtract 2 from both sides, and that will give me this final solution, negative 2 plus or minus the square root of 3. So finally, that brings us to the quadratic formula, and this is arguably the most complicated of all the methods, but it has the advantage that it can be used to solve any quadratic equation. So to use it, you have to start by identifying the values of the three parameters, a, b, and c. And those are just the coefficients of the polynomial in order. For example, looking at this first equation, a is the number in front of the x squared, b is the number in front of the x term, and c is the constant term. Now remember that you should include any negative sign, so the value of c will be negative 4. So to solve this equation, all I have to do is substitute those values into the formula and simplify that result. And that'll give me x equals negative 4 plus or minus the square root of 4 squared minus 4 times 2 times negative 4 divided by 2 times 2. The part under the square root simplifies to 16 plus 32, or just 48. 48 is equal to 16 times 3. So the square root part simplifies further to 4 times the square root of 3. And if I reduce that by 4, I'll get the final answer. X equals negative 1 plus or minus the square root of 3. Now, the second equation will follow the same pattern, but notice that there's no number in front of the x squared. Remember that when a number isn't written, you can put a 1 there. So this gives us a equals 1, b equals 5, and c equals negative 1. And if I substitute those values into the formula, it becomes negative 5 plus or minus the square root of 5 squared minus 4 times 1 times negative 1 over 2 times 1. So the square root part here simplifies to 25 plus 4, or just 29. And that can't be simplified any further, so our final answer is negative 5 plus or minus the square root of 29 divided by 2. Now, I described this equation as an eventually quadratic equation because while it may not look like a quadratic equation yet, with a little manipulation we can make it into a quadratic equation, which will be nice because then we can use our quadratic equation solving methods to get its solution. So what I'm going to do is I'm going to multiply both sides by x squared. The right-hand side just stays 0. And on the left-hand side, I'll distribute the x squared into the parentheses by multiplying all of the terms inside the parentheses by the x squared. Now, what happens with all of the x squareds? On the last term, the 2x squareds cancel, and we're left with -3. On the middle term, x divided by x squared is just x, so we're left with 2x. And the first term, x squared, is just x squared. Now, this equation looks like the quadratic equations we were talking about on the previous slides. The polynomial factors to x plus 3 and x minus 2. And I can solve this equation by setting those two factors equal to 0, giving me these two linear equations. The first one gives me x equals -3, and the second gives me x equals 2. So those will be the solutions of the quadratic equation and of the original rational equation. So on this slide, I have an application from physics that's used in fields like ballistics. This equation describes the height of an object that's been fired from an initial height with an initial velocity after it's been in the air for t seconds. Now, in this specific example, we have a mortar that's been fired from the ground with an initial velocity of 168 meters per second, and we want to know how long it's going to take for it to make it back to the ground. Now, the first thing I'm going to do is replace some of the parameters in the equation with information from the problem. For example, the object is being fired from the ground, so its initial height is 0, and its muzzle velocity or initial velocity is 168. So that makes the equation s equals -4.9 t squared plus 168 t. Now, what we want to find is the time when the mortar reaches the ground. In other words, the time when its height is 0. So if I replace s with 0, that will give me a quadratic equation. If I factor a t out of the equation, it becomes t times -4.9 t plus 168. And I can solve this by setting the two factors equal to 0. The first one gives me t equals 0, which we already knew. That means that the mortar is on the ground at time 0, which is when it's being fired. And the second one tells me that the mortar is back on the ground when t equals 168, -168, divided by -4.9, or after approximately 34.3 seconds.